Modern enterprise networks are built on a simple premise: cables break and hardware fails. To survive these inevitable points of failure, network architects wire redundant physical links between switches to keep data moving. But at layer 2 of the OSI model, redundancy creates a severe architectural danger. Without logical management, tying switches together with multiple active links creates an infinite loop. When a broadcast frame enters this kind of uncontrolled topology, it is endlessly duplicated and forwarded out of every port. This triggers a broadcast storm, where data packets circulate in a continuous loop until they consume all available bandwidth and crash the network. The original engineering solution to this problem was the spanning tree protocol, or STP. STP maps the entire network topology and logically blocks specific redundant interfaces. This forces all traffic down a single loop-free path. The redundant cables remain in place physically, but they are disabled logically. The protection works, but traditional STP has a critical flaw: its transition logic. When a network topology changes, like a severed active cable, STP relies on strict, rigid timers to detect the failure and calculate a new path. This recalculation process can take up to 50 seconds. During that window, the network drops traffic completely, severing active application connections and halting communication. To eliminate this latency, network engineers developed the Rapid Spanning Tree Protocol, or RSTP. Looking at this timeline comparison, by redesigning how switches transition and communicate, RSTP drops that recovery delay down to a fraction of a second. Modern infrastructure requires the network architecture to manage loop prevention without compromising real-time data availability. To understand how RSTP achieves this speed, we first establish what the protocol leaves untouched. In this standard 3-switch network, the foundation is the root bridge, the central switch anchoring the topology. Once elected, non-root switches calculate their absolute shortest path back to this anchor. Any links outside this optimal path are logically blocked, breaking the loop. Both legacy STP and modern RSTP utilize this exact same election and path cost process to construct a safe Layer 2 environment. The core difference between the protocols is not the final network shape, but the absolute speed at which the network adapts to reach it. Maintaining a single logical path requires a consistent central reference. RSTP accelerates the failover process while keeping this election process intact. The primary cause of legacy STP's severe latency is its complex multi-stage state machine. Looking at this transition flowchart, an interface running legacy STP must idle through distinct blocking, listening, and learning timer phases before finally forwarding data. These mandatory delays were engineered decades ago to allow slow, early-generation network hardware enough time to safely process topology changes. RSTP addresses this bottleneck by collapsing those legacy states. The old blocking and listening phases physically merge into a single, unified discarding state. In discarding, the port actively monitors the network but halts user data. Next is the learning state. It populates MAC-address tables but still drops user frames. Finally, the interface enters the forwarding state, becoming fully active and securely routing user data across the network segment. By mathematically reducing mandatory transitional states, RSTP eliminates the forced idle time that crippled legacy network recovery. Beyond shrinking the state machine, RSTP gains even more speed by predicting hardware failures before they actually occur, through specific port designations.
Let's look at a single non-root switch. Its primary active interface, providing the absolute best path up to the root bridge, is the root port. Conversely, an active interface forwarding traffic outward for a specific local segment is the designated port. RSTP achieves this speed through a mechanism called pre-calculated redundancy. Instead of waiting for a primary cable to snap, RSTP proactively assigns formal standby roles to the links it has blocked. The first is the alternate port, a pre-calculated standby path leading up to the root bridge. It remains locked in the discarding state to prevent loops, but continuously monitors the primary root port for failure. The second standby role is the backup port, providing redundancy on a shared local segment when multiple paths exist from the same switch. To separate the two, the alternate port protects the upward path to the root, while the backup port protects the downward path to the segment. The advantage is precise. If the active link is severed, the switch already knows its exact next move. It doesn't pause to recalculate the map.
By pre-assigning these backup rules, RSTP turns network failover from a reactive, slow calculation into a proactive, nearly instantaneous switchover. There is one final structural optimization RSTP uses to eliminate connectivity delays, specifically for endpoints. This diagram isolates two distinct connections on a switch. Port A connects to another switch, while port B connects directly to an end device, like a server or printer. RSTP designates port B as an edge port. The logic behind this classification is simple. Unlike a network switch, a server or PC does not internally bridge network traffic. Therefore, the device characteristics of a server make it impossible to inadvertently loop a layer 2 network back onto itself. RSTP utilizes this topological property. With zero loop risk, the edge port transitions immediately into forwarding, bypassing the discarding and learning states entirely. The practical result is that servers, workstations, and endpoint hosts experience instantaneous network connectivity the second they are plugged into the switch or booted up. By applying strict logical rules based on the type of connected device, RSTP surgically removes security bottlenecks where they aren't topologically required. When we bring together the root bridge foundation, the streamlined state machine, and the pre-calculated port roles, we can observe exactly how RSTP handles a catastrophic failure. Here we have a functioning redundant topology. User data routes smoothly along the active primary root port, while the alternate port sits quietly in standby. Then a sudden hardware failure severs the primary uplink cable. The active path is dead, and traffic halts. Recognizing the severed link, the switch instantly calls upon its pre-calculated contingency plan. The alternate port jumps directly into forwarding. Because it already knows it provides a safe path to the root bridge, it bypasses the legacy timers and takes over traffic routing. Legacy STP successfully solved the problem of redundant architecture, preventing disastrous layer 2 loops, but it did so at the heavy cost of operational latency. RSTP provides the exact same loop prevention mathematics, but it operates at the speed required by modern data centers. It achieves this performance by consolidating the transition state machines, applying zero-delay logic to edge ports, and configuring intelligent standby roles. By optimizing how switches negotiate paths and detect failures, RSTP guarantees that enterprise networks remain both entirely loop-free and continuously highly available.